rubber bands. Dadgum, always somebody, right?
Oh my goodness.
Was it Bennett? I don't know.
What did I do?
Did you forget to record it?
You know what you did?
You're a scapegoat. All right, so it says use linear regression on your calculator to find the regression line. Guess what? It's already there for you, so don't worry about it. This is the line that best models the data. All right, in the video, when I do the TW notes, I get into really the technicals of this regression line, why it's called least squares regression line. It's not something you have to remember. Calculator does it for you. But it finds the best straight line to fit the data the best. Does that mean it's going to hit every single point? No. It's just the best one, all right? And it tries thousands of them instantaneously. So here's our best fitting line right here. So what's my slope here? There you go. Slope is always the number with your x, right? It's always your slope. And then the other one is the y-intercept. So there's my slope, y-intercept. All right. So here's the nice thing. TW uses Excel. They don't use the calculator. Yeah, it's awesome. So in the video, I'm going to show you how to read the Excel output to find your slope and your y-intercept. All right. It's not as obvious as this, but it's not hard. All right. So make sure you see that in the video because that's the way it's going to show up on your quiz and your final exam, which I have no control over. But it's not hard. You've made it this far. That's a piece of cake. All right. Now, it says use the regression line to predict the distance that Barbie travels for 5 rubber bands. Since we don't know, we can use that line to make a prediction. All right, so how do you suppose we would use the line to make the prediction? 5 represents the number of rubber bands, right? So input 5 for x. So let's do that.
I'm gonna give these back.
Oh, all right. All right, so we crank that out. Plus 25.333. And I get 62.65. And this group is in centimeters. Does that make sense with the rest of the data? Seem logical? Reasonable? Yeah, somewhere between 55 and 69.
Yes.
Makes decent sense. All right, so seems like it's a good prediction. Now, one of the group members found the measurement for 5 rubber bands. Their actual measurement was 64. Okay, that's the actual. Remember what we just found here is a prediction, right? Are predictions correct always? No, they're just a good estimate, right? Now, was the prediction from number 2 too high or too low? Too low. And by how much? Well, too low. So to find out how far off it was, I would take the actual and subtract the predicted. So actual was 64. Subtract that. $1.35. So we call this a residual. Okay? How far off was the actual point from the predicted? All right? And it's not that hard to figure out because if you think about your scatter plot, here's your dots, right? And my prediction line, oops, that's terrible. My prediction line does the best it can to predict it. But if my actual point, let's say this is my actual point right here, it's higher than what the line predicts, what I'm finding is this distance right here from actual to predicted. This is that distance we just found by subtracting, all right? And that's what we call the residual. If it's positive, that means the actual was higher than the line would have predicted. If it's negative, that means the actual is lower than the line would have predicted. That's all it means. All right? So if I were interpreting this, I would say the actual distance traveled is 1.35 centimeters higher, because it's positive when I subtracted, 1.35 centimeters higher than predicted using least square regression line, and we definitely abbreviate that, LSRL. So it's just a good reminder that line is just a predictor. It's not gospel truth. All right, you ready for 4? All right, it says predict the distance that Barbie would travel if the group had used 20 rubber bands. All right, let's do that. So it would be, let's use that line again. Y equals 25.333 plus 7.464 times 20, right? Let's see what we get.
ST what?
122. .61 centimeters. All right. Does that make sense to you? Yeah? All right, so the next question is, would you trust this prediction more or less than the prediction that we made up in number 2? It's a thinker. You say less? Why would you say less?
Because it's a bigger number than the first one was. The first one was a smaller number, so it means that your prediction can be more accurate the bigger that you get.
Why would the smaller number be more accurate? You're on the right track, for sure. It's just finding the right words. Why would the smaller number be more accurate than the bigger numbers in this case? Anybody want to help her out? Huh?
Does it have something to do with marginal?
Nobody wants to help out. Nobody? Nobody? All right. Here's the kicker. Look at the data collected. How many rubber bands did we go up to when we actually collected data? 7. So this regression equation is only based on 7 rubber bands. It only goes that far. It's only predictable up to 7. Anything outside of that, we don't know the line is good, because maybe that line that was going straight up kind of goes down. Remember how we said outliers can pull it down and change it up? We don't know what's going to happen. So your regression line is only as good as the data set it came from. So if you try to predict outside of it, that's called extrapolation. It's a really bad idea. We don't do it. All right, it's bad form, they would say. All right, so let's write that down. Would it be less? It would be trust it less because 20 rubber bands is outside, let's say, the scope of the data. And we call that extrapolation. Can you actually plug in 20 and get a number? Yes, you just wouldn't rely on it as strongly. You would kind of give it some warnings like, wouldn't trust this as much. All right. So let's go back then to our equation, original equation. What did you say the y-intercept was? 25.333, and in this case that represents centimeters, right? So here comes stats. What does this y-intercept mean in context of the question? Remember what y-intercept means in algebra? It's where the line touches the x-axis, right? Where x is equal to what? 0. So what does x equal in the context of this question? It is 0, but 0 what? 0 rubber bands, right? So what does this mean? It means that if Barbie has 0 rubber bands attached, the distance she would fall is 25.333 centimeters. Basically her height, right? She would just faceplant. Let's go. Does that make logical sense? Yes. Sometimes when you interpret y-intercepts, it will not make sense. Like, sometimes y-intercepts can be negative, right? So if this happens to be negative, it's like if Barbie has no rubber bands, her distance fall would be a negative number. Does that even make sense? No. So although we interpret it with x as 0, it may not make logical sense, may not be a reasonable conclusion. So you just have to keep your thinker on and be reasonable. All right. And realize, what is this telling me? This saying if x is 0, then whatever y in context is, that is your y-intercept. We'll do another one, don't worry. Slope of the equation. What was our slope? 464. All right. Now, what does this mean? This is where the context comes in. All right. So here's how you would say it. I'm thinking. For each additional rubber band attached, the predicted distance traveled will it increase or decrease? How do you know? It's positive, right, in our equation? It will increase by 7.464 centimeters. So when you interpret a slope, it's always for each additional something, in this case, rubber band attached. And then distance traveled is our y value, right? Context. Everything else stays about the same. So it's just about taking your good old Algebra 1 equations and put meaning on it. That's all it is. Can we live with that? All right. Here it is. Here we go. Predictions. Okay, so we use this equation. Notice it says y hat. That hat means it's a prediction. All right, the predicted y. It's not. It's just the guarantee. It's just saying this is not a guaranteed. It's just a prediction. Y hat is equal to, and there's your equation. That will be provided either in Excel or your calculator. So we would write the equation in the context of the variables, or define the variables. So if you write it like this, just say x equals number of whatever and y equals, like in this case, the distance of the fall, right? Define the variables. And we want to be careful because although you can make predictions with your line, you want to be careful of extrapolation, where we're making predictions outside the scope of the data. You don't want to do it. Okay, and then there's finding residual values. So residuals is always going to be in this order. It's always the actual value minus the predicted. All right. Now the predicted is usually, you have to find it using the equation. Use the LSRL equation to find the predicted. The actual will be given to you, either like in the problem setup, paragraph, whatever. Can you not read it? It's okay. It's either in the problem setup or it's like in a table. They will give you the actual. You have to find the predicted, and then you have to subtract in this order, A minus P, not P minus A, right? So then if you're interpreting that, you would say the actual, and you would put the response variable in context. Actual distance following was your residual value, whatever you get, higher or lower, depending on if it's positive or negative, than the predicted value for x equals whatever your explanatory variable is. So the actual distance following was 1.33 centimeters higher than the predicted for x was 5 rubber bands. Okay? And then the last little bit, this is a lot of interpretations today, isn't it? Well, the good news is you only have one more left. That's it. All right, next thing is interpreting slope and y-intercept. With slope, we would say with each additional x in context, whatever your x value is, the predicted y, and then you would say increases or decreases by, and then your slope value. All right, and then if it's the y-intercept, you would say, when I'm going to put x equals 0, but x, you would put this in context. When the number of rubber bands is 0, the predicted y variable, distance falling in context, is, and then you put the y-intercept with units attached. 26.33 centimeters, whatever. All right, I know it's a lot, I know. But you won't have a lot of these. You just got to remember these kind of ideas. All right, let's try this one out. Michael's a runner. He uses his Apple Watch to keep track of his distance and the number of calories he burns for 20 runs. Scatter plot of y equals calories burned and distance in miles shows a fairly strong positive linear relationship. Regression line is there. Y hat equals 20 plus 160x. Models the data fairly well. Interpret the slope of the regression line. All right. So using my interpretation sentence up here, we say with each additional, what is x this time?
160.
No, what in context? In context, what is my x value?
The distance.
Yeah, distance right there. Okay. There it is. Okay. I know. For each additional mile run, right? Great things coming. All right. The predicted, what's the response variable here? What is the miles predicting here?
The calories burned.
Calories burned, thank you. Will it increase or decrease? Increase by how much? By 160 calories. Because my slope is 160, right? Is that okay? B. Okay, I always do this in different order. It says, does the y-intercept have meaning? Interpret the y-intercept. If not, explain why. So I always interpret it first and then stop to think. Does that even make sense? All right, so let's do that first. So if I'm doing y-intercept, okay, when? What is x in this scenario? Miles run, right? When no miles have been run, the predicted Response variable is calories burned, right? Is, what's my y-intercept? 20 calories. If no miles are run, he only burns 20 calories. Is that logical? Does that make decent sense? Yeah. All right, so does it have meaning? You would say yes, has meaning, or it might say, is this reasonable? Just depends on how it's worded, but it's kind of the same idea. It has meaning. So if it, if your y-intercept was negative, that wouldn't make any sense, would it? No. C, predict the number of calories that Michael burns if he runs 5 miles. What does that mean I need to do? Plug it in, plug it in. So let's plug it in. Y hat equals 20 plus 160 times 5. Show your work, always. So I get 820 miles. Or not miles, what is it? Calories. D says, calculate and interpret the residual. If his Apple Watch said that he burned 910 calories on a 5-mile run. So residual, remember, is always the actual minus the predicted. So which of my numbers here, I have 910, which one's the actual? 900 is the actual. The predicted is what we just did right here, isn't it? And thankfully, usually they put those in order for you, so you've already done the work. So actual would be 910 minus 820. Was that 90? 90 calories difference. So then I have to do the interpret piece. The actual calories burned is 90 more or less. More than predicted by the least square regression line, LSRL, when x equals 5 miles. Michael's thinking about signing up for his first marathon. So far, the longest run he's done is 10 miles. Should he use the regression equation to predict how many calories he's going to burn in a marathon, which is 26.2? No, why not? It's not within the scope of the data. Everybody agree with that? What do we call that? Extrapolation. Extrapolation. No. So we'd say no, this would be 26.2 miles is outside the scope of the data. So any prediction you make would be unreliable. Bad news bears. Don't do it.